So he is a PhD student. He's working for Zhongwei Zhu and Alan Yule from John Hopkins University, I guess. So he has been working a lot on the 3D CTs, especially he's been pioneering a lot of works in abdomen CT, especially multimodal CT models. So today I think he's going to give a talk about his last ICCV paper. Would you like to start, Pedro?
Yes, thank you very much. So let me share the screen. Okay, can you see my screen?
Yep.
Okay, so today I will present about Abdomen Atlas 3.0. That is our paper that just got accepted at ICCV. And this paper was done at Johns Hopkins University with the collaboration of Ibrahim Sezgin and supervised by Professor Alan Yu and Dr. Zhongwei Zhou. And basically, this paper introduces a new data set. And what's unique about this data set is that it is the first large-scale abdominal CT data set that has CTs, tumor segmentation masks, and radiology reports. So let me begin starting about the data problem that we have for abdominal CTs. So public abdominal CTs, they do not have many tumor annotations. The largest ones have about 400 annotations for each tumor type. And by annotations here, I mean segmentation masks, per voxel segmentation masks of the tumors. None of these public data sets have radiology reports on abdominal CT. For chest CT, we do have a data set with reports. That's data set from Ibrahim. But in abdominal CT, it's different. So for this reason, we have very few visual language models available for abdominal CTs. Basically, we have two right now. There is Merlin from a group at Stanford, and it's trained on private data. And there is M3D that is not trained on private data, it's trained on public data. However, it's not trained on the hospital standard CT scans. Instead, they got data from the internet. So their CT scans are not really 3D objects. They are a series of 2D pictures. So we lose the information, for example, about the distance between these slices, between each one of these pictures. And also the captions are not really radiology reports, but they are extracted from the web. So in summary, there is a lack of data to train large vision language models that could do report generation and VQA for abdominal CTs. And that's where our data set comes. We introduce here Abdomen Atlas 3.0, which is a data set with CTs, radiology reports, and tumor segmentation masks. We have 3,000 CT scans with tumors. Each one of them has a report and a segmentation mask. We focus on three types of tumors, liver, kidney, and pancreatic tumors. And in total, our data set has 9,000 CT scans. And here we compare it against other data sets, and you can see it's in a larger scale. And also, it's the only one with radiology reports for abdominal CT. Some characteristics of our data set, we have not only one report, but two reports for each CT scan, because we have a structure reports and also a narrative free text reports. I will show examples and explain more of these two types later. Our data is completely public, so it was gathered from public sources, from public data sets, and it includes 138 institutions, medical institutions across the globe. So that's very nice for generalization. We have a very diverse set of data from many continents. We have three types of tumors, and another important data that we have is organ subsegments. So we have subsegments of the liver and the pancreas. In other words, we have segmentation masks for parts of the organ. For example, for pancreas, we have the pancreatic head, the pancreatic body, and the pancreatic tail. You may ask, why is this important? This is important because this changes knowing which part of the organ the tumor is important to understand how it will develop, the best treatments for it, and the best surgery for it. For example, for liver, surgeries can remove one of these subsegments without affecting really the others. So it's very important to understand really in which subsegment the tumor is. We also have annotation segmentation masks for blood vessels around the pancreas. And this is again important for surgery because by checking how the tumor touches this blood vessel, we can understand how easy it is to remove this tumor or if it's unremovable. So the blood vessel annotation is important for staging, and we are also the first data set with staging for pancreatic tumors. In total, we have 8,000 tumor instances. So we have 3,000 tumor CTs and 8,000 tumor instances because one CT may have more than one tumor, and a very large number of small tumors, more than 5,000, which is very important for early detection. Here is an example of one of our structure reports. In summary, a structure report, it is based on a fixed template, and a group of radiologists create this template. And it's important to have this structure because it provides a standard format and a standard terminology to describe the findings in the CT scan. And this allows better understanding between different institutions and more complete reports. So by following the templates, you do not forget or miss some important information. And also studies show that in the end, it leads to better medical decisions. So we have standards, structure reports following a radiologist created template for all of our data. However, we also have narrative reports. Narrative reports are free text reports. So instead of having this separation organ by organ and of very strict structures, it's written in free text. And it mimics the standard writing style of radiologists in major hospitals. Why we have that? Because many hospitals still do not adopt structured reports. So by providing also the narrative reports, we allow people to train in our data sets and create visual language models that also can write narrative style of reports, allowing wider applicability of these models to different institutions and their preferences. Now, let's start talking about the data set creation. So the first step to create Abdomen Atlas 3.0 was creating segmentation masks for the tumors. Not only do we aggregate many public segmentation data sets, we also provide many tumor segmentation masks for them. So many of these data sets were not originally tumor segmentation data sets. They were organ segmentation data sets. So they did not have tumor annotations. Here in this table, in the numbers before the arrows, you see the number of tumor annotations that these reports had. And after the arrows, you see the number of annotations that they have now, because we had a team of radiologists look at the CT scans and provide tumor segmentations for this data. And this group of radiologists could increase the number of tumor segmentation masks in this group of data sets by 3 times. So in total, we went from 300 liver tumor CTs to 900. 190 pancreatic tumors to 344, 450 kidney tumors to 1,674. So that was a large increment, and all of this data, as I mentioned, is public. So we have all these annotations, these masks for the public, and we also have the reports for them. Other important aspects of our data set, it's the only 2 data sets have liver subsegments, ORS and deletes. ORS is larger than the alternative one. For pancreas subsegments, we are the only public data set that provides the segmentation masks. We tried a lot to get these kinds of data from other data sets, even looking for MRI, but we could not. Now we are providing them. We are the first one to include the blood vessels around the pancreas. So we have segmentation masks for these blood vessels. And this is very important to understand the stage of tumors, because how the tumors touch and interact with blood vessels change how severe they are. We have the tumor stage for pancreatic tumors, and we have radiology reports, which the other datasets do not. Now, how did we create these reports? That's the question. So what I talked about until now was the segmentation part. So we created these tumor segmentation masks for the entire data set. We had first an AI model do some preliminary pseudo labels for these tumors in the CT scans. We provided these to the radiologists, and we asked the radiologists for the ground truth segmentations for these tumors. In many cases, they did it from scratch because they preferred it. In other cases, they improved the segmentations we provided by the AI. And in the end, what we got was these 3,000 ground truth tumor segmentation masks. And then we needed to create the reports. In other words, we needed to translate the tumor segmentation masks into radiology reports, into language, into text. We could have tried to use AI to do this, but we wanted to really ensure that the information in the radiology report really matched the information in our ground truth segmentation. So we created our structured radiology reports not with AI, but with deterministic algorithms. So we have rule-based algorithms that read the segmentation masks, extract information from the segmentation masks, and write it into a template to create the structured radiology report. So in detail, we have algorithms that determine the tumor and the organ size, the tumor and the organ attenuation, so how bright the tumor is in relation of the organ to the organ, the tumor and the organ volume, the contact of the tumor with other organs. So did the tumor grow out of its original organ and started touching other organs? And also the degree of contact between the tumor and blood vessels, which is very important to determine the severity, the stage of the tumor. The tumor stage itself, we also extract from the segmentation. And if the tumor is resectable or not, can it be removed by surgery or not? And finally, the tumor location, so in which organ, in which parts of the organ the tumor is. We extract all this information through the deterministic algorithms that are really explainable, so you understand why they extracted this information, and we use this information to fill templates provided by radiologists. Then this is the template-based, the structure reports. So how do we go from that to the narrative free text report? Then we use large language models. So basically, we take the structure reports, we give it to LLM, a zero-shot LLM. Here it's Llama 3.170B. And we also give this LLM many examples of human-written narrative reports from a large hospital. And we ask the LLM to change the style of our structure reports to match the style of this large hospital. So by style, we mean the words used and the structure of the reports. And we do a special selection of examples for this in-context learning idea, and in meaning that we select examples that are similar to the structure reports we are trying to convert. So if we have a structure report about liver tumors, we take 10 examples of liver tumor reports from the institution, give the LLM, and ask it to do this style adaptation. After it does the style adaptation, we want to check if the narrative reports have the same findings as the structure reports. Because remember, the findings of the structure reports came directly from the human-made segmentation. So we have a consistency check. We have a second LLM compare the two reports and see if the findings, the medical findings, are the same among them. And finally, we have a human revision step to check if these new reports match the original ones. But the main human work in this pipeline is to do the segmentation. Then the rest becomes pretty straightforward and simple. Okay, so here I'll talk a little bit about some of our deterministic algorithms to extract information from the segmentation masks. So first, how do we measure tumors? Ideally, you want to measure tumors the same way that radiologists do. So what we did is we created an algorithm that implements the World Health Organization standards for measuring tumors. Basically, it will go slice by slice in the CT scan, the Z slices, and it will find the slice with the largest diameter. So for each slice, we calculate the maximum distance between 2 points in the tumor border, and that's the diameter of the tumor. So for the slice with the largest diameter, we take this diameter and the perpendicular one. And in the report, we add these two, we write down these two diameters. This follows the way radiologists measure tumors. And our another important deterministic algorithm is the staging algorithm. So this is the pancreatic staging algorithm. And basically, to determine the local stage, the T stage of the tumor, two information are very important. The first one is the size of the tumor, which we measure as I explained right now. So smaller means smaller stage. But another very important information is the degree of contact between the tumor and the important blood vessels around the pancreas, meaning the SMA, the CA, and the CHA. These three important blood vessels. And what we do is we have an algorithm that walks through the vessel, and at each point, it finds the perpendicular plane, and it measures how much of the blood vessel borders in that plane touches the tumor. And using that, it calculates the degree of contact. So we look at the degree of contact across the whole blood vessel, and we check which is the maximum degree of contact between the blood vessel and the tumor. If it's smaller than 180 degrees, like is shown in this image here, it's not the tumor is not encasing the blood vessel. If it's larger than 180 degrees, it is. In this case, it's very hard to remove this tumor because you cannot easily cut the blood vessel. And in this case, the tumor is T4, the highest local stage, and it's not resectable. So in this case, the patient needs to do some radiotherapy, for example, to try to reduce the tumor. If it's not T4, the patient may go directly for surgery. So it's very important to know this information because this influences the treatment of the patients. Yeah, this is an example of a report for pancreatic tumor, and we measure this degree of contact between the tumor and many blood vessels, as you see here. For the SMA, the superior mesenteric artery, this tumor, it's completely the blood vessel is completely inside the tumor, as you see in this image. So we have 260 degrees of contact between the tumor and the blood vessel, which means this tumor is the highest stage, it's T4, and we write this down in the reports. Another important algorithm that we have is how do we create pancreas subsegments, because as I said, it's very important to know in which parts of the pancreas the tumor is, because this influences treatment as well. And no other data set has this subsegment mask. So we cannot easily train that in another data set and apply here. So what we did is, again, we tried to see how radiologists do it and implement an algorithm to do the same thing. So we have segmentation masks for the whole pancreas and for the SMA, the superior mesenteric artery. And this blood vessel, the point where it begins marks the division between the head of the pancreas and the body of the pancreas. So basically, we take the segmentation, we align the pancreas horizontally with PCA, we find this point where the blood vessel begins, and we cut the pancreas at this point. So here we have the head, here we have the body. Then we take the remaining, remove the head, take the remaining pancreas, and find again the half point. And this half point is the division between the body and the tail. And again, this is a way to divide the pancreas that is accepted by radiologists. So we follow their procedures, but we create an algorithm to do it deterministically. And here, for example, you see that we find a tumor in the head of the pancreas and write it down in the report. For liver, also the subsegments are very important, but for liver, we had a public data set with this information, so we could train a segmentation model in this data set and use it to find the liver subsegments in our data sets and do some active learning to improve it a little bit. And we could create it in an easier way than the pancreas subsegments. Now, I talked about our structure reports or narrative reports, but there is a third type of report that we have in our data set. In this case, we only have 240 of these reports, not 9,000 like the other ones, which is the enhanced human reports. What do I mean by enhanced human reports? Well, as you can imagine from my talk until now, the reports that I mentioned until this point are based on the segmentation. So we use the segmentation to create the reports. And this is based on tumor segmentation. So the main focus of these reports are tumors. They have much information about tumors, but not the other findings that we can see in human-made reports. So what we do for 240 samples of our data set, we have human-made notes or reports about these CT scans. Some of them come from public data sets, and some of them were written by our radiologists. And what we did is we asked a large language model, again, the same Llama 3.1, to fuse the information in the segmentation-based reports, which we call the RadGPT reports, and in the human-made radiologist notes. And it joins these two reports, creating a single enhanced human report, which has all the information both in the segmentation-based reports and the human report. So for example, here you see a lesion in the kidney that came from the segmentation-based reports, and you see a finding about plaques in the coronary artery, which came from the radiologist notes. As you see, these plaques have nothing to do with tumors, so they were not in our segmentation-based reports, but now they are in these enhanced human reports. And why do we call these enhanced human reports? Are these better than human reports? In some aspects, they are. So we compared these reports to reports in a major US hospital, and we find that our reports always measure all of the tumors that were found in the CT scan. So if the CT scan has 10 tumors, we'll have measurements and locations and detailed information for each one of them. However, the human-made reports, normally they will only have this information for the largest tumors. So almost 40% of human-made reports mentioned tumors, but do not provide measurements for them. Also, our reports provide HU values, numerical HU values for all tumors, and human-made reports do not. And our report provides the volumes of tumors, while human-made reports only provide the diameters of the tumors. But the volumes are important. They are highly correlated to the advancement of the disease, but they are very hard for humans to measure. However, with segmentation masks, they become easy to measure. Okay, so until now, I talked about this pipeline that generated our data sets. We call it RadGPT, and we mainly conceive it as a data set generation pipeline. So a way to use human-made segmentations of tumors and convert them into radiology reports. However, we may also change this pipeline, remove the human participation in it, and then we have a fully automatic report generation methods. So in this case, what we do is we take the CT scan, we do the segmentation of tumors and organs, and we follow the pipeline as we had before. We just remove the human revision of these segmentations, and we create the reports fully automatically. What's the advantage of this approach? The advantage of this approach is that semantic segmentation of tumors is a really advanced field. So many people have worked in this for more than one decade. So for many years, we had the community focusing on this task, and the accuracy is very high if you compare to the newer fields of vision language models. So what we want here is to translate this high accuracy of segmentation into report generation. And we do that with the same pipeline that we use to create the dataset, but removing the human revision. And again, this deterministic extraction of information for the segmentation ensures that if the segmentation can find the tumor will be in our reports. Now, how do we evaluate reports created by visual language models, and how do we compare our model, RadGPT, against other models? Many works use standard text similarity metrics used to evaluate large language models to evaluate report generation. However, there is a problem here because these text similarity metrics, they are strongly influenced by the style of the reports. So if you look here, you see that our structure reports have a RUG1 performance of 0.14, but the narrative reports have 0.24, which is double. However, the medical contents of these two reports are exactly the same. So we should not see a difference so strong between these metrics. So what we propose is a simple way but a trustable way to evaluate these reports. We evaluate basically the capacity of the visual language models to find the tumors. And we use what the community has used for many years, that is sensitivity, specificity, and F1 score for tumor detection. But how do we do this with reports? So we have the AI-made reports and a ground truth human-made reports. We use a zero-shot LLM, again Llama, to analyze both. And we basically ask the LLM, does this report show a hepatic tumor, a renal tumor, or a pancreas tumor, yes or no? And we use this LLM to convert basically the reports into binary labels. And with these binary labels, we can calculate the standard metrics, sensitivity, specificity, F1 score. You may ask, how accurate is the LLM? That's a good question. And we have evaluated it manually using almost 450 reports. And we found it had an accuracy of 96%, which is pretty high and comparable to standard labelers in big data sets. And to get this high accuracy, we have worked for a long time in our prompts with many iterations with radiologists to improve the prompts and really tell the LLM how can it define if a report shows a tumor or not. So now we come to the final results table, and we compared our RadGPT against a large part of the state-of-the-art in visual language model for CT scans. Here, our RadGPT is the fully automatic method, so no human involved in this one. And it is based on segmentation. And what we see in these results is we have two test data sets first. The first one is IID, meaning it's a random split of our Abdomen Atlas 3.0 data set. And the second one is evaluation in an external hospital, so a hospital that was never used for training, so OD evaluation. And what we see is that in both cases, RadGPT surpasses the state-of-the-art in finding the tumors. And the reason, again, is because you can say it's cheating, because we are using the strong segmentation models and transforming the information from this segmentation, tumor segmentation, into reports. So basically, RadGPT inherits the high performance of these tumor segmentation models, and that's the reason why it can beat the state of the art. And the other models we have here are CTChat, CT2Rep, M3D, Merlin, and RadFM. And CTChat and CT2Rep, if you compare to the other models, excluding our segmentation-based model, they perform really well on these two data sets. Another in relation to the other three. And another interesting finding is when you compare the internal and external validation here, you see that the segmentation-based report generation model, it does not lose much performance when you go to the unseen hospital. However, the vision language models, normally they do lose quite a significant amount of performance when they go to the unseen hospital. And we think that the reason is that segmentation has a strong generalization capacity. And this translates in our case, to a strong generalization capacity of our reports. And
you mind if I ask a question?
yes, sure.
So is your model, is it trained on the reports? And so is it trained or is it zero shot?
So my model, go back here. It's basically trained on this segmentation. And we transform the segmentation into the reports. And the segmentation, we use only the Abdomen Atlas 3.0 dataset. So basically, my model is not trained with the reports. They are trained with segmentation and transforms into reports. Other models here are trained with the reports. So in this case, we had CT-Chat, CT2Rep, and M3D trained with Abdomen Atlas 3.0 reports, and Merlin and RadFM are zero shots. No, sorry, Merlin is also trained with the reports, sorry. RadFM is zero shots, and M3D is zero shots.
So just to clarify, it takes the segmentation, converts it to a report?
Yes, exactly.
So
exactly.
the mask is an input and then the report would be the output?
No, the CT is the inputs. Then we have a segmentation model creates the mask. And then we have the deterministic attributes extraction creates the reports.
So you're evaluating, I guess, the deterministic aspect. So what would you specifically be evaluating?
We evaluate the reports, but the performance of these reports match the performance of the segmentation because of the deterministic algorithm.
I see. So it's mostly evaluating the segmentation model.
Yes.
How well you're converting
yes.
that model.
Yes, you're right. Yes, exactly. Okay. So I think that's basically
You want to
it.
ask now?
Feel free to ask questions.
Yeah, you showed this table and then you said like that the segmentation models generalize, and you probably mean something very specific by saying that, but I was not sure what you mean like in this context.
So by generalize, I mean this first data set comes from this first test data set comes from the same sources as the training data sets. So it's the same data distribution as the training data set. This one below, the external validation, comes from a totally unseen hospital from UCSF. This hospital, no CT scan of this hospital was used for training. So that's why it's more difficult evaluation. You need to generalize better to another population of patients, another type of CT scanner, for example, to be able to perform well in this second data set. It's more challenging.
Just as a follow-up, like how big was it? Like, did you check all of this, if it's really a shift in population, and if yes, what was the shift as well in scanners?
It's a little bit difficult to check the shift because as our data sets, the IID data set comes from public data. Many of these public data do not have the information about the scanner and all these important metadata. However, we are very sure there is a big shift because, for example, a large part of our training data set comes from Asia, much for China, for example, and this external test data set is all from one hospital in the US. So there is a shift in population for sure.
Maybe a follow-up to that table. You're showing sensitivity and specificity, but for some models, it feels like a bit arbitrary for RadFM not finding anything at all and then having specificity really high. Do you also like measure F1s or stuff like that, which might like compensate a bit more for that?
We do have F1 in the paper, but not in this main table. But yeah, you are right. For some models, it seems they were not able to find many tumors. For example, here RadFM. Basically, it could not find any of these tumors here. So that's why we have specificity super high and sensitivity super low. But keep in mind, this is a very difficult task because we are asking a large vision language model to analyze a CT scan and find a small tumor. So this is the tumor is a really small thing inside the CT scan, and segmentation is really good at that. But large VLMs.
How exactly do you like measure the accuracy though, like sensitivity? Do you have your like report and then you extract from the report if it said there is something?
Yes.
But localization it does not provide you, right? So it just says there is something somewhere. Do you ground that somehow, or is it just
what we did in this big table is to use this LLM to analyze the reports. So it will check if the tumor is reported or not, and in which organ the tumor is reported. So we analyze per organ. So we check if does the ground truth report show a tumor in the kidney, and then we check does the AI made report show a tumor in the kidney. We have more fine-tuned evaluations. So for example, checking if the sizes are correct, but for that we did not use LLM, we used radiologists, and then the data set size was much smaller because we needed the radiologists to check each one of them.
So thank you.
Thank you.
Yeah.
Okay.
Yeah. Max, another question?
It's not a question, but I just wanted to say, like, we see exactly the same, by the way, in X-rays, that sometimes we wonder if, like, we need an LM or actually want a structured report that just lists certain findings, right? Like, you could also think about a classifier, and then you take all the outputs and then convert it into text. We never really tried that, but I think that's a very reasonable approach. And yeah. Maybe in general, like, not sure if it's too much of a open question. What do you think about the use of LLMs in this context? Do you see, especially for CT reporting, do you see a task where this would be very useful, or do you think in general it's a bit misleading to try to use LLMs for that?
I don't
You don't have to answer if that's a
I do not think it's misleading. I think, yes, we should have LLMs involved because LLMs can do things that the classifier or the segmenter can't. You can ask questions for it. You can do VQA, so you can expand it to new tasks. But the challenge is how can we make the accuracy of the LLM match the accuracy of a segmentation or a classification model? And what our results suggest here, and that's our direction right now, is to try to fuse the segmentation and the LLM. So can we use segmentation to extract information and give this information to the LLM? So really a two-step approach. We think that can really create an LLM that can do many tasks that the segmentation can't, but at the same time provides the high performance of the segmentation to the LLM. So that's our current vision.
Yeah, I just had a quick question about the LLM classification approach. So I was just wondering, so I actually was working on a very similar project. So we had some similar challenges where we're trying to convert the report to kind of classification metrics. So I noticed in this case, you did zero shot with the LLM. Did you consider fine tuning the LLM? Because that was something that we kind of validated and we found that that was a little bit better.
That's interesting. Our fear of fine-tuning the LLM was it's an open question. Will it generalize well to new hospitals or not? Because I think it mostly depends on your data set. So if you have a very large data set with many institutions and reports for many institutions, then I think, yes, fine-tuning will be great because you can learn from this, and then because you have this big data diversity, you can generalize well. But if you have a single hospital, I would be a little bit afraid if you fine-tune, you may lose generalization to new hospitals in the future. In our case, we did not have many human written reports for many institutions, so we went for the zero shots approach. and we manually evaluated it, and we find it could get very high accuracy if we spend a long time improving the prompt and talking to radiologists and giving the prompt a good explanation of how the LLM should evaluate the report, what's a tumor, what's not a tumor.
Thank you.
Yeah, thank you so much, Pedro. Thank you so much for the presentation. I think that Abdomen Atlas 3D0 is a great resource for our 3D research. And also the benchmark, I think, is very useful because I think it shows that it proves that the naive VLMs are not enough for clinically deployable models. So if you want to get some models that can be clinically deployable, I think we need more clinically aligned approaches like yours. So especially for the small abnormalities, like nodules, like tumors here. So I think we need to design more grounded approaches, more specialized approaches for that clinically deployable models. So thank you so much for your time and for visiting us. Thank you so much for your talk. So
Thank you very much. Yeah, and I fully agree with that.
Okay, goodbye.
Thanks a lot.
Bye.
thank you.
Nobody was finished.
Catch you again.